In this lecture, we will see some applications of the Liret-Hirsch theorem. So we will begin by showing that Pn plus 1 minus the point is a line bundle over Pn. So this is complex. So note that we have already seen the projection from a point map. So that's denoted by phi. Is given by so let Wi contained in Pn plus 1 denote the open set Zi not equal to 0. Then then let Ui contained in Pn denote the open set again Zi not equal to 0. Then phi inverse of Ui is exactly Wi. And we may write phi as, so here I is not equal to n plus 1. So phi on Wi. So this is coming in the ith place. So this shows that Wi is isomorphic to Ui cross C, where the projection onto C is given by the function Zn plus 1 by Zi. So let Wij contained in Uij cross, well, Wij contained in Wi be the subset Zj by Zi not equal to 0. So then Wij is exactly equal to uij times c. And there is a commutative diagram. So given by so this is in the ith place. So this is now in the jth place. So the vertical arrows are the projections, and the horizontal arrows are multiplication by z, zi by zj. So uh, so note that if we fix a point x in uij and y in uji denote its image, then the top horizontal map, so this goes from is linear on the fibers, on the fiber. So thus we conclude that we have a line bundle on Pn on complex projective space whose total space is the union which is Pn plus 1 minus 1 point. So let us denote this line bundle by L. So the zero section Pn clearly corresponds to the hyperplane. Zn plus 1 equal to 0. In Pn plus 1 minus this point. So let L prime be L minus the 0 section. Then L prime is Pn plus 1 minus a hyperplane, but Pn plus 1 minus a hyperplane is Cn plus 1, and we are removing the point, the origin from it. So this is homotopic to S2n plus 1. From the long exact sequence of pairs L comma L prime, we get H to k minus 1 So let's assume k lies between 1 and n. Then since L prime is homotopic to the sphere, these two terms are 0. Thus this middle thing is an isomorphism. L being a vector bundle over PNC, its deformation retracts onto its 0 section, which is isomorphic to PNC. Thus H2k of L is isomorphic to Z. Thus H2k of L comma L prime is also isomorphic to Z for k lying between 1 and n. So we have the restriction map H2L comma L prime to H2LP L prime P. So here P is a point in Pn, and these are the fibers LP and L prime P. So we want to show that this map is an isomorphism. So our aim is to apply the Leray-Hurst theorem. So first we see using excision that so here T is a disk bundle on P and C, and S naught is the zero section. So the picture looks like this. Here we have P and C, and here we have our line bundle, and this is the zero section. So we can take a region like this. So one way to do this rigorously is we can put a metric on the fibers of L, and so this is the projection map, and take vectors of norm less than equal to 1. So this, of course, the zero section is this. So T minus S naught deformation retracts onto an S1 bundle, which we denote by thus we have as S1 is a deformation retract of a neighborhood in the disk bundle. This implies H2 of but note that T with S1 collapse, the sphere bundle collapse to a point is the one-point compactification of the interior T naught. So there's vectors in the fiber of norm strictly less than 1. As L is homeomorphic to T naught and L is equal to Pn plus 1 minus 1 point, this implies the 1 point compactification of T naught is Pn plus 1. So we have a commutative diagram of pairs So this is the fiber of L over P, fiber of L prime over P. Inside L we have a disk, a D2 of vectors of norm less than equal to 1. And here this is the disk bundle and the S1 bundle. This in turn maps to comma a point star, which is the image of the S1 bundle. This maps to D2 mod S1 comma star. So this gives on cohomology So we have maps like this, and all these vertical maps are isomorphisms. So let's number this, and let's call this map 3 prime. So we want to show that 1 is an isomorphism. So it suffices to show that 4 is an isomorphism. So it is clear that the inclusion of T2 mod S1 into T mod S1, the sphere bundle, is the same as the inclusion of P1C into Pn plus 1, given by the line which is the closure of phi inverse P. So this is true up to a homeomorphism. So thus 4 is the pullback on cohomology induced by the inclusion of a line So it is clear that I induces an isomorphism on the homology H2. For example, we can check this using CW homology. So give Pn plus 1 a CW structure in which the 2 skeleton is the image of I. So thus I lower star from H2 P1C to H2 Pn plus 1 C is an isomorphism. So the universal coefficient theorem and the naturality of maps there show that there is a commutative diagram and the horizontal arrows are isomorphisms. So this implies I upper star is an isomorphism. So this implies 4 is an isomorphism. So this implies 1 is an isomorphism. So the group H star LP L prime P is isomorphic to H2 LP L prime P, and this is isomorphic to Z, and we have found a class theta in H2 L comma L prime such that theta restricted to the fiber in H2 LP comma L prime P generates it. Thus, we can apply the Liret-Hirsch theorem and we get H star P and C tensor Z theta. So let's say this free abelian group generated by theta to H star L comma L prime is an isomorphism. In particular, this shows that H2K Pn to H2K L tensor H2 L comma L prime, and here we are at the cup product pairing. Alpha maps to P upper star alpha tensor theta, and this maps to P upper star alpha cup theta is an isomorphism. So we claim that there is a commutative diagram So this follows easily from lecture 21. So see the commutative diagram at the end of page 2. And the diagram D1 on page 3, and deduce the above using similar arguments as given there. So now we consider the diagram. So let's call this box. So this is identity tensor box. So let's give this equation a name star. So by equation star, the vertical arrows are isomorphisms when k lies between 0 and n minus 1. So this shows that h2k pn to h2k plus 2l, we have alpha goes to p upper star alpha cup theta. So theta is image of under this isomorphism. So this is an isomorphism. And now we can take the 0 section, pull back along the 0 section, so this composite is an isomorphism. So the second arrow is pulled back by the 0 section. So note that P compose S naught is equal to identity. But theta was chosen to be a generator of, so we have this group H2 L L prime, And theta was chosen to be a generator of H2LL prime, but this is isomorphic to H2L, and by P upper star, this is isomorphic to H2PN, which is isomorphic to Z. Thus, we can fix a generator theta naught in H2PN, a generator, and take theta to be the pullback of P upper star theta naught. Then the above says that H2K PNC to H2K plus 2 PNC alpha maps to alpha cup theta naught is an isomorphism. When K lies between 0 and n minus 1. Thus, the cohomology ring of P and C is isomorphic to Z theta naught mod theta naught to the n plus 1, where theta naught is in degree 2. So let's see some more applications. So let e to x be a vector bundle. Then we have the projective bundle, so we denote this also by P. So as an application, of the computation of the ring H star PNC and the Leray-Hirsch theorem, we want to compute the cohomology of P of E. So we will only sketch the main steps involved. So given a continuous map, f from y to x, we have a pullback vector bundle which sits inside this diagram. And the fiber of f upper star E at a point y is canonically identified with the fiber of E over f of y. If phi from V to W is an isomorphism of vector spaces, so then it induces a canonical isomorphism from the space of lines in V to the space of lines in W. So here P of V is equal to V minus 0 modulo the action of C star is the space of lines in V and has the quotient topology. If E has been constructed by gluing Ui cross Cn plus 1 using maps phi ij's, then P of E can be constructed by gluing Ui cross Pnc using maps phi ij tildes, which are from Uij's to odd Pnc. So one easily checks. So the phi ij tilde is the tilde corresponding to is the tilde which appears in step 2. That these satisfy the cocycle condition. Let denote the bundle map. So the fibers of P are given by P of E sub x is equal to lines in E sub x. So there is a line bundle which we denote O P of E minus 1 on P of E, which is a sub-bundle of P upper star E. That is, there is an inclusion which has the following description. So let both these are vector bundles over P of E. Let L in P of E be a point. Let P of L be equal to X. Then this point L is in the fiber over X. Then the fiber of, so let's call this map J. J over the point L corresponds to the inclusion of L sitting inside E sub X. So recall P upper star E, the fiber of this over L, is canonically identified with the fiber of E with the point P of L, which is equal to E sub X. If y to x we have a continuous map, then we have a commutative diagram. And the pullback F tilde upper star of O of this inclusion is equal to the inclusion on P of F upper star E. So these were some general facts about vector bundles and projective bundles. For a line bundle, L on a topological space M, we can define a cohomology class which we denote C1L in H2MZ. And suppose F from N to M is a continuous map, then this definition satisfies the condition F upper star of C1 of L is equal to C1 of F upper star L. So the construction of C1 has the following property. So let O of PV, so here V is a vector space, minus 1 denote the bundle in step 4. So where we have just x is just a point, then C1 of OP of V minus 1, this is a class in H2 of P of V, comma Z, is a generator. So we will apply the Liray-Hirsch theorem. So note that each fiber is complex projective space, and so the cohomology is a free abelian group. Thus, the first hypothesis of the theorem is satisfied. So consider the class theta so by point 6 theta restricted to P of E sub x is equal to C1 of OPE minus 1 restricted to P of E of x. This is using point 5 C1 of OP of E sub x minus 1. This is using point 7 theta naught, which is generator of H2 P of Ex. Since 1 theta naught up to theta naught to the power n is a z basis for the cohomology, H star Pn C, it follows that 1 theta to theta n in H star P of E satisfy the second condition of the Liray-Hirsch theorem. Thus, the canonical map so E is a bundle of rank n plus 1 This map is an isomorphism. So that is, we can look at the image of the map, that is I equal to 0 to n, p upper star of h star x, cup with theta I. And this direct sum is equal to h star of p of e. So in particular, the class theta n plus 1, there's an h 2n plus 1 of p of e, can be written as an expression in the LHS. Since theta n plus 1 has degree 2n plus 2, it suffices to consider the elements of degree 2n plus 2 in the LHS. Thus we get where alpha I are in h2i x. So we can rewrite this as where CIE belongs to h2i x. So this identification is possible. As p upper star is an inclusion. So the classes CIE are called the Chern classes of E. So we will end here, and I will give some references for some of the other steps for anyone who is interested in more details.